Now that we have the idea of a linear combination, we want to look at all of the possible linear combinations once I have a set of vectors. So the span of a set of vectors a1 through am is the set of all of the possible linear combinations of these vectors. And this is how it's denoted, the span of a1 through am. Like I said, these are all the possible linear combinations. So a linear combination is just a single vector that's written using a combination of scalar multiplication and addition. The span is all of these possible linear combinations. So here I have a matrix, and I want to actually describe the span of the columns of this matrix. So let's look at how to do this. So in order to do this, we're going to put this in an augmented matrix with just a general vector as the final column, this ABC. And so to be able to describe the span, we need to know when this solution exists. If I start to reduce this matrix, this is what I get over here on the right. And this will always have a solution, in particular because I have a pivot in every single column. And since this always has a solution, there's no conditions in the span. Instead, the span of the matrix is all of the vectors in R3. This time I have a set of vectors, and I want to describe the set of vectors. And this is going to work just like the last example. We want to put these in a matrix with this general vector in the final column. So once we do that, we then need to reduce the matrix and see when a solution exists. And when I reduce it to row echelon form, this is the matrix that I get over here on the right. And we can now say that we have a row of zeros. So we want to know when this solution actually exists. So our condition for the vectors is that we need to have negative 2a minus b plus c is equal to 0 for the vector to be in the span. So these examples have been using the idea of this theorem. A given vector b is in the span of vectors a1 through an if and only if there's a solution to the equation ax equal to b, where A is the matrix formed using a1 through an as the columns. So like I said, this is the theorem that we've been using to do our previous example, so let's see if we can prove it. Let's suppose B is in the span of the vectors to start with. By definition of the span, that means we can write B as a linear combination of these vectors a1 through an. So by a theorem that I proved in the last video when I talked about linear combinations, this means that ax equal to b does have a solution, where the A matrix is formed using these vectors as its columns. Now that we've done that, let's look at the other direction. So this time we're going to suppose that ax equal to b does have a solution. By something shown in my last video, that means that b can be written as a linear combination of the columns of A. And by definition, since b is a linear combination of the columns, it belongs to the span of the columns. So therefore, we've proven this theorem.